we have to study about the two types of polymerization. First is addition polymerization or chain growth polymerization. Now in case of addition polymerization involves successive addition of the monomer units to the growing chain carrying a reactive intermediate such as the free radical, a carbocation and carbanion. This type of the polymerization is called chain growth polymerization, and the polymer thus formed are also called chain growth polymer because it takes place in a stage leading to increase in the chain length, and each stage produce a reactive intermediate for use in the next successive stage in the chain. Now the free radical addition polymerization takes place when we observe a variety of unsaturated compounds such as alkene and their derivatives. They will undergo the polymerization in presence of radical initiator such as dioxygen, benzoyl peroxide, acetyl peroxide, tertiary peroxide, etc. The polymerization of the ethene is carried out at high temperature 350 to 570 Kelvin and high pressure 1000 to 2000 atm in presence of dioxygen and a small amount of the benzoyl peroxide as a radical initiator. Now it will take place in three steps: initiation, chain propagation and chain termination. Now in initiation step we will observe that the first step 1, the growing free radical chain get terminated by the reaction which consumes these free radicals either by combination or by disproportionation. These are called chain termination steps. Now in chain initiation, the benzoyl peroxide changes into benzoyl free radical and which is able to generate phenyl free radical. This phenyl free radical react with alkene and changes into big free radical. Now after this, the propagation of the chain will take place, and when the propagation of the chain will take place by coupling or by combination of the two free radicals, we are able to get the chain termination, where we are getting the terminated chain as we have already shown in the slide. The termination of the free radicals will take place. Now this results in the formation of the two types of the polythene. One is known as the low density polythene and other is known as the high density polythene. In case of low density polythene, it is manufactured by heating ethene at 350 to 750 Kelvin under a pressure of 1000 to 2000 atmosphere in presence of traces of oxygen and peroxide. This polymerization occurs a free radical mechanism which is initiated by oxygen or peroxide molecule and forms low density polythene. Low density polythene is a transparent polymer having moderate tensile strength and toughness, chemically inert, slightly flexible and poor conductor of electricity, while high density polythene is generally obtained by the coordination polymerization using Ziegler-Natta catalyst for the polymerization of ethene at the temperature of 343 Kelvin and pressure of 6 to 7 atmosphere. And in case of Ziegler-Natta catalyst, we are taking triethyl aluminum and titanium trichloride as a catalyst. This type of polythene is translucent polymer. It is chemically inert, having great toughness, hardness, tensile strength, etc. Second is Teflon. Teflon is also known as polytetrafluoroethene. Teflon is manufactured by heating tetrafluoroethene in presence of peroxide or ammonium persulfate as a catalyst under high pressure. Because of the great chemical inertness and high thermal stability, Teflon is used for making non-sticky utensils. A thin layer of the Teflon is coated on the inner side of the utensils. It is also used for making gasket, pump, packing, valve, seal, non-lubricating bearings, etc. Next is polyacrylonitriles. It is known as Orlon and also known as PAN, 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 polyacrylonitrile. The addition polymerization of acrylonitrile in presence of peroxide catalyst gives polyacrylonitrile. Now the polyacrylonitriles are used as a hard, horny and high melting material. It is a substituent of wool in the manufacture of Orlon or acrylic fibers, used for making clothes, carpet, blanket. It is also used in the preparation of other polymers to improve their quality. Next, we will get the condensation polymerization or the step growth polymerization. In this case, we have to study about the formation of the polyesters like terylene. Now the terylene are the polymers which have high ester linkages, therefore we call them as polyester, and prepared by the condensation of polymerization diacids with diols. Here we are taking ethylene glycol and terephthalic acid. The terylene or dacron is the best known example of polyester, prepared by the condensation polymerization of ethylene glycol and terephthalic acid with elimination of water molecule. The reaction is carried out at about 420 Kelvin in presence of the catalyst, consisting of the mixture of zinc acetate and antimony trioxide. This fiber of terylene is highly crease resistant, durable and has low moisture content. It is also not damaged by the pest, moths and other insects. It is therefore used for manufacture of wash and wear fabrics. It is used for making tire cords, seat belts and sails. The mylar film is extensively flexible, tear resistant of ultraviolet damage degradation, and it is also used for making magnetic recording tapes. Now polyamides. These polymers possessing amide linkages and are important example of synthetic fibers and termed as nylons. Here we will discuss about the two types of nylons, that is nylon 66 and nylon 6. Nylon 66 is prepared by the condensation polymerization of hexamethylene diamine and adipic acid under high pressure and at high temperature. Nylon 66 is used for making sheet, bristles of the brushes and in the textile industry. Nylon 6, it is obtained by heating caprolactam with water at high temperature. Nylon 6 is used in the manufacture of tire cords, fabrics and ropes. It is also used for making ropes used by the mountaineering pupils. Preparation of polyester, as we have already discussed about the terylene. Now come to the phenol. Preparation of phenol formaldehyde polymers. Phenol formaldehyde polymers are the oldest synthetic polymers. These are obtained by the condensation reaction of phenol with formaldehyde in presence of either acid or a base as a catalyst. The reaction starts with the initial formation of ortho or a para-hydroxymethylphenol derivatives, which further react with phenol to form the compounds having rings joined to each other through the CS2 group. The initial product would be the linear product known as Novolac used in paints. This is a structure where we see the phenol show the condensation reaction with formaldehyde in presence of acetic and basic to form orthohydroxymethylphenol, and 2,4-dihydroxydimethylphenol, 2,4,6-trihydroxytrimethyl when on linear combination of orthohydroxymethylphenol, we are able to get the novolac. The novolac on heating with formaldehyde undergo the cross-linking to form an infusible solid mass called bakelite. It is used for making combs, phonograph records, electrical switches, and handles of the various utensils. The next is melamine formaldehyde polymer. The melamine formaldehyde polymer is formed by the condensation polymerization of melamine and formaldehyde. It is used for making unbreakable crockeries. Now the copolymerization. In this process, the polymerization reaction in which the mixture of more than one monomeric species is allowed to polymerize to form a copolymer. This copolymer can be made not only by the chain growth polymerization but by step growth polymerization also. It contains multiple units of the each monomer used in the same polymeric chains. For example, mixture of 1,3-butadiene and styrene can form copolymers. Here the two monomers are styrene and 1,3-butadiene. They will copolymerize in presence of sodium as a catalyst to form BuNaS. This is the natural rubber. As we know that the natural rubber has a high degree of elasticity. It is also termed as the elastomer and has a variety of use. This rubber is also known as the rubber latex, which is the colloidal dispersion of the rubber in water. The natural rubber may be considerably as a linear polymer of isoprene, that is 2-methyl-1,3-butadiene. It is also used as cis-1,4 polyisoprene. Now, why the vulcanization is required in the case of natural rubber? The natural rubber becomes soft at high temperature above 335 Kelvin and brittle at low temperature. On vulcanization, sulfur forms cross linkages at the reactive site of the double bonds and thus the rubber gets stiffened and probably structures of vulcanized rubber or the molecules are depicted below. As we know, the natural rubber is a soft, sticky and become even more so at high temperature and brittle at low temperature. Therefore, rubber is generally used in the temperature range of 335 Kelvin where its elasticity is maintained. It has a large water absorbing capacity and has low tensile strength and low resistance to abrasion. It is also not resistant to the action of the onyx solvent and is also easily attacked by the oxidizing agent. These properties can be improved by the process known as vulcanization. As we have already seen in the case of the slide, it consists of heating of the natural rubber with sulfur at 415 Kelvin. Since this process is slow, therefore the additive like zinc oxide are also used to accelerate the rate of the vulcanization. During vulcanization, sulfur bridges or cross linkages between the polymer chains are introduced either at the reactive sites. And after this vulcanization, the following changes takes place in the case of the rubber. The rubber become hard, much stronger and lose the water absorbing capacity and also possess a high degree of elasticity. Now we will get the improvised rubber after the vulcanization. This is the synthetic rubber which is known as the neoprene. Neoprene is a polymer which is formed by the polymerization of chloroprene. Under high temperature and pressure, we are able to get the neoprene. Neoprene is formed by free radical polymerization of chloroprene. Neoprene is inferior to natural rubber in some properties but superior in its stability to the aerial oxidation. And it has resistance to the vegetable or mineral oil and is therefore used in manufacture of gasket and shoes, heels and stoppers, etc. BuNaN. Buna N, it is also known as the nitrile rubber. Buna N is obtained by the copolymerization of 1,3-butadiene and acrylonitrile in presence of peroxide as a catalyst. Here letter N in Buna N stands for acrylonitrile. It is resistant to the action of petrol, liberating oil and the onyx solvent. It is therefore used in making oil seal, hoses and tank lining. Now come to the biodegradable polymer. The biodegradable polymer is known as polybeta hydroxybutyrate co-beta hydroxyvalerate, which is known as PHBV. It is obtained by the copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. PHBV is used in specialty packing, orthopedic devices, and in controlled releasing of drug. PHBV undergo bacterial disintegration in the environment. Now this is the table in which we are having the name of the polymers, monomers, their structural unit and the uses. First is polypropene. The monomer is propene. Manufacture of rope, toys and pipe and fibers, its uses. Polystyrene, the monomer is a styrene and its uses are insulators, wrapping material, manufacture of toys, radio and television cabinets. PVC, monomer unit is vinyl chloride, manufacture of raincoat, handbags, vinyl flooring, water pipes. Urea formaldehyde resin, monomers are urea and formaldehyde for making unbreakable cups and laminated sheets. Galactyl, monomers are ethylene glycol and phthalic acid, manufacture of paints and lacquers. Bakelite, monomers are phenol and formaldehyde, used for making combs, electrical switches, handles of utensils and computer disks. These are the contents that we are present or showing the representation in the case of the polymer. Thank you.